Hey there! Ever wondered how scientists untangle massive, messy data to find real patterns? Today, we're exploring a game-changing statistical technique that's helping researchers make sense of complex problems, like figuring out what really influences health outcomes or economic trends. Let's break down how this research is reshaping the world of data analysis. First, let's talk about beta regression. Imagine you're studying something that's always between 0 and 1, like the percentage of people with health insurance in a state, or the fraction of a city's budget spent on education. Traditional methods like binomial models need to know the total number of trials, like how many people were surveyed. But what if that number is missing, unreliable, or just not applicable? That's where beta regression shines. It's like a flexible tool that works directly with proportions, no extra info needed. Cool, right? But here's the twist. What if you're dealing with hundreds or even thousands of variables, like income, education, healthcare access, and more, while only having a few hundred data points? That's the high-dimensional problem. It's like trying to solve a puzzle with more pieces than the box shows. Traditional methods struggle here because they can't handle the complexity. Enter Lasso penalization, a technique that shrinks less important variables to 0, helping us focus on the most relevant ones. Think of it as a spotlight, highlighting the key factors. But here's the catch. When you apply Lasso to beta regression, the math gets tricky. The equations aren't straightforward because the model's landscape is full of hills and valleys, non-convex. It's like trying to find the lowest point in a maze with no clear path. The researchers tackled this by developing a new framework to analyze these tricky, stationary points near the true answer. They proved that even in this messy landscape, their method can still get close enough to the real values. Mathematically, they call this a non-asymptotic bound on the L1 error. Basically, they showed how accurate their estimates are, even without assuming infinite data. But wait, there's more. They also created a way to build confidence intervals for their results. Lasso can sometimes bias estimates, making them less reliable. Their debiasing approach fixes this, giving us a clearer picture of how confident we can be in each variable's impact. To make this all work, they designed a special algorithm called a proximal gradient method. It's like a step-by-step guide for navigating that non-convex maze, balancing the complexity of beta regression with the simplicity of Lasso. And guess what? They tested it with real-world data, like social justice studies, proving it works in practice. So what's the takeaway? This research isn't just about fancy math. It's about building tools that cut through the noise and find meaningful insights. Whether you're analyzing health data, economic trends, or social patterns, these methods help us see the forest for the trees. Thanks for watching and stay curious, because the world of data is full of surprises. Hey there! Ever wondered how scientists and mathematicians make sense of super complicated problems, like predicting patient outcomes from hundreds of medical metrics? It's like trying to find a needle in a haystack, but instead of a needle, you've got 1,000 tiny, glittering fragments. Today, we're diving into the math that helps us trust the tools solving these puzzles, m-estimators. So imagine you're building a model to predict something really tricky, like whether a patient will respond to a treatment. Traditional methods, they can get lost in the noise. That's where m-estimators come in. They're like smart filters, sifting through the data to find the most important patterns. But here's the catch. How do we know these filters are reliable? That's where the real math kicks in. The researchers behind this work created a framework to prove these estimators work under certain conditions. At the heart of it, a key assumption called A3. Think of it as a rule book for the math. One of the rules is making sure a value called kappa stays positive. Why? Because kappa acts like a safety margin. If it's too small, your predictions could go haywire, like a car with no brakes. But if kappa is just right, it keeps everything under control, even when the data is noisy or messy. Now let's break down the tricky part, a term in their equations labeled 13. It's like a puzzle with two pieces. The first piece deals with the data we actually see, and the second. That's the rare wild stuff, like a storm in a calm sea. For the wild stuff, they use a technique called the union bound. Imagine checking every possible way things could go wrong, and making sure none of them actually do. By setting a threshold U based on kappa and some math about logs, they show those extreme cases are so tiny, they're basically invisible. The real magic happens with the first piece, the data we see. Here they tackle something called an empirical process, which is just a fancy way of saying, how well does our model match reality across all possible scenarios? To simplify this, they use Rademacher symmetrization. Think of it as flipping a coin to average out the noise. By randomly assigning positive or negative signs to data points, they turn a messy problem into something manageable. It's like using a mirror to see the data from all angles at once. But wait, how do they make sure their model does overreact to tiny changes? That's where Lipskitz's constants come in. These are like speed limits for functions. They measure how sensitive a model's predictions are to